ahead and get started. Welcome everyone to this webinar on creep strength enhanced ferritic steels, which today will be mainly dealing with grade 91 material. Just to let you know, we are planning on a lot of future webinars. Some of these may be related to material metallurgy, some tube failures. So I hope you'll join us for those. So yeah, my name is David Nesbitt. I've been with ATC CES for about 7 years, and previously spent 36 years working in the power generation industry for TVA. I work on boiler and heat exchanger assessments, failure analysis, root cause analysis, project support, and so forth. The other gentleman presenting today, Dr. Joe Zhao, is Chief Metallurgist here at ATC CES. And he worked previously for Alstom and CE, and he'll fill you in on his credentials a little bit later in detail. Jeff Henry, who many of you know, was not able to be with us due to another commitment. So with that, just a quick little overview of what ATC CES is. You know, ATC was started in the mid-90s by Harley Grant to do material coatings, both spray and by gas diffusion, and also heat treatment in the shop. A small metallurgical lab was incorporated, and later engineering support was added to the company. So in 2019, CES and our Combustion Engineering Solutions, which was named after CE, was started to increase the emphasis on engineering and metallurgical services. With the closure of the Alstom Metallurgical Laboratory here in Chattanooga, several other personnel and a lot of the lab equipment was brought to CES. So the engineering services include condition assessments, piping, structural analysis, training, litigation support, root cause analysis, project support. So that's where we are as a company. Today, our agenda. Of course, this is introduction, followed shortly here. Dr. Joe Zhao will be given a brief introduction of grade 91, and then a pretty thorough presentation on the understanding of metallurgical differences between grade 91 and traditional steels. We'll follow it up by a little shorter presentation on inspection techniques, and after that we'll follow up with Q&A. Share that. I'm learning this new technology here. I forgot to share it, so. Okay.
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 My turn.
Just a few logistics before we move on. We have no dedicated breaks, so if you feel like you need to get up to go to the bathroom and get a cup of coffee, feel free to do that. If you were not on the mailing list and you'd like to be added to the mailing list, just add your name and your contact information in the chat. And lastly, for the Q&A session at the very end, if you would, as you think of questions through the presentation, put them in the chat, and we'll follow up during the Q&A session. So with that, without further ado, here's Dr. Joe.
Okay. You guys put in the mute. All right. Good morning. Good evening for the friend from China. Okay, I'm going to give 2 talks. One is very brief, about a brief introduction of grade 91 development, research, and our experience in ATC CES. Okay, so this is going to be a first talk. Just a few slides. Okay, oh, too quick. Okay, sorry. Okay, so I'm going to start with introduce myself a little bit. Then I'm going to talk about the Green 91 development. I'll be finished talking about the Green 91 research and our experience. Again, my name is Gang Zhou, so everybody can call me Joe, okay? So currently I'm working as a chief metallurgist for ATCCS. This since March of 2017. Before that, I was working for Alstom GE in the Materials Research Center in Chattanooga, Tennessee as the principal metallurgist for 15 years. Before I joined Alstom, I was working and study at the University of Tennessee Materials Joining Group under Dr. Carl Londing, okay? Green 91. Green 91 is developed by combustion engineering at their MATLAB. So the gentleman I would like to mention, his name is Ted Ward. Okay, he is the grandfather of Green 91. He wrote the first proposal to DOE in 1969 to developing super 9-chrome material for sodium-cooled nuclear reactor. Okay, so this proposal has been approved in 1975 by DOE. Then Oak Ridge National Laboratory joined the program as the DOE agent. So you may, if you guys know Green 91 well, reading a lot of Green 91 early development material, you probably run into a lot of Oak Ridge National Laboratory reports. Take about 5 years, 1975 to 1980s, to establish the composition and a favorable microstructure, then leading to the excellent materials property. Okay. Later in the program, Japanese Mitsubishi joined the program to testing the Green 91, also studied the weldability, formabilities. Okay. 91 was accepted by ASME as cold case 1943 in 1984. Since then, the research, okay, so by that time, the Green 91 has been fully developed. But the research on the 91 is never stopped, okay, has been continued until now. So since 1980s, there's a team of the metallurgists continues working with Ted on the Green 91. So the main focus is one is the long-term creep strength and behavior of Green 91. The other one is effective fabrication practice on the creep strength and the behavior of Green 91. This because the Alstom is one of the OEM to manufacture all the power generating equipment. So all the OEM has been understanding how to manufacture Green 91, maintain the properties. Okay, so and this is including the composition of the base material, forging behavior, heat treatment. Okay, so for by co-working effect, heat treatment effect, welding, post-weld heat treatment. Okay, so then when you talk about welds, then you have a type 4 creep damage, stress corrosion cracking, low ductility, fracture behavior, okay? And in the last 10 years, people are seeing more and more failures on the Green 91 DMW joint, okay? So this is not a hot topic. Okay, so here's a quick list of the CES engineering have been published, the reports, documentations, and technical reports related to 91 or creep stress enhanced deferring materials. Okay, so bunch of every report. Okay, so we also have hundreds of technical report on failure analysis, condition assessment, well repair of creep stress enhanced ferritic steels component. Okay, mainly is the power generating equipment, including tubes, pipes, okay, any equipment using in the power industry. Okay. So I like to highlight a few cases. Currently, we are still working on the Green 91. One is a DOE project on the T91 ID chromizing. Okay, as everybody knows, okay, there's a lot of T91 superheater or with heater assembly now is in operation. Okay, there's a lot of case reported is because the ID steam scale exfoliation trigger a lot of scale build it up on the bottom band, okay, and then leading to overheating event. Okay, so developing this program by diffusion of chrome from tube ID surface, create a thin layer of chrome-rich layer, then we can stop the steam scale activation. Okay, so this is one case we are still going. The other case is CES has been working with one of the Chinese steel, we're developing this unique T91 integral fan tubing. So what this is going to do is, when the power generation efficiency go up, okay, pressure, temperature go up. So more and more 91 will be using building membrane panels, okay, like a lot of CIB unit now, even in the superheater. Okay, so if you're using the traditional panel structure, you have to using a membrane bar with the 4 longitudinal wells. So for 91, as everybody knows, so if you weld it longitudinal on the tube surface, then you create a type 4 zone. Okay, so the type 4 zone weld strength reduction factor is 50%. Okay, so that's going to be penalize how you applicate the T91 tubing to construct the panel component. So what this unique tubing going to do to you is we are moving the welds onto the pre-built fan. So previously, each tubing you had welded 4 longitudinal welds. Now you only can do just 1 pass or 2 passes. This not only solve the type 4 zone issues on the tube wall, and also solve the issue, can save a lot of construction or manufacturing dollars. The last case I will share you is, later on I'm going to talk about more on this area, okay, is a new methodology to determine the Green 91 metallurgical condition, okay, mainly is on the subsurface. Okay, 91 is using tempered monazite microstructure. Okay, optically, you cannot see much of substructure details. Traditionally, how people do the study is using TEM, okay, so TEM sample is so small, you only can view about a 0.2 millimeter zone around a 3 millimeter diameter sample. Okay, to study a general condition, especially when the material is highly ununiform, you're going to run through 20, 30 samples to really pin down the case. So that each TEM sample costs you $3,000. Okay, so you can imagine it also is very time consuming. Okay, need a lot of effort. Okay, it's not everybody can using it. So what we try to do is, one, now Zeiss has the ICM has an inline function. Okay, so allow us to do the quantitative metallography. So as you can see on the picture, okay, on the first line, the second and the third picture, they are 10,000 and 50,000. You can see the details on the Green 91 substructure, okay? So we try to establish a pattern for each Green 91 condition. For example, normal 91, for example, soft 91, for example, if the 91 run past A1 temperature, okay? There's many different conditions we're going to study. So when this method established, we'll be using as a tool to looking at your in-service component, whether they are in the correct condition. So I think they will talk about a part of these things on a different methodology, how to determine the Green 91 conditions. Okay. The other thing we can use for this methodology is try to predict Green 91 when main life. Okay, by looking at green 91 substructure is removed from the surface. Okay, so we can, and that is going to taking a lot of creep testings, interrupted creep test. Then we can stop that. Then we can see when you reach 20% life, this is the microstructure. 50% life, this is microstructure. To see how this microstructure is going to degrade in the surface condition. Okay, so this needs a lot of pre-ground work to establish this pattern. So now we are just beginning to do this thing, but it's going to take a lot of time. Okay, this basically covered very quick review to cover to see what is going on the green 91, how the 91 being developed. Okay, so touch upon is the importance of the green 91 material. Okay. Hey, Dave, I'm finished the first one.
Gotcha.
Okay, so I'm going to start the second one. Okay.
Okay, proceed.
Okay, the second one, what I'm going to talk about is the fundamental understanding the metallurgical difference between green 91 and the traditional chromoly steels. Okay. So what I'm going to start is the DNA of the material. Okay, all called the DNA of the steels. Okay, and here, what's the common steel microstructure? Okay, then we're going to touch upon the steel strengthening mechanisms and heat treatment. Then we're going to talk about the difference between 91 and the chromoly steel from compositions, heat treatment, microstructure, and properties. Okay, then we're going to close up with remark. What is the DNA of the steel? Okay, as you know, microstructure. Okay, so I'm going to explain why the microstructure is the DNA. Okay, so on the bottom, I show you three microstructures. On the right-hand side, that's called the pearlite. That's commonly seen in the carbon steel. In the middle one is tempered bainite, as commonly seen in the T11 and T22. On the left-hand side, that's a typical T91 microstructure. Okay, that's a tempered monazite. Okay. So what is the microstructure? Okay, so when the metallurgist to design a steel, the first thing they're going to design a microstructure. Then what is microstructure? Microstructure basically is two parts. The first part is the matrix. Okay, for steel, either ferrite or austenite. Okay, so when we're talking about creep stress enhanced ferritic steels, the matrix is a ferrite. Okay, ferritic steel. Okay. Then the second part is called precipitates. Okay, so this part is a little bit complicated. That's including what type of the precipitate. So you can look at carbides, nitride, carbon nitride, Z phase, Lauer phase, sigma phase, chi phase, pi phase. There's a ton of them. Okay, so it also the precipitate is talking about types and shapes. Okay, can be laminar, can be particle, can be needles. Okay, the size from micron up to nanometers, okay? And also influence the interface structure is between the matrix and the precipitates, okay? Either coherent, semi-coherent, or non-coherent, okay? And also influenced by how this precipitate distributed, either in the matrix or is on the grain boundary, okay? The one big issue on this precipitate is the thermal stability. And this is also influence on the creep behavior. So if you have one precipitate give you a good properties on the room temperature, when you put it in the water is running at 1,000 degrees or 1,050. You know, so when in the elevated temperature, okay, so the microstructure are going to be beginning to degrade. Mainly degradation is the precipitates. Okay, precipitate is going to grow up. And the size is also going to change in the interface structure. Okay, so this has been, a lot of people have been studied this. Why microstructure is important? Okay, is because the microstructure is governing the properties of the steel. Okay, so even people say, okay, when I buy the steel, I really want the property. Okay, But as a metallurgist, okay, so they have to know what's the microstructure of the steel, okay, because the microstructure gave the properties of the steel, okay. Now, how steel achieve a microstructure, okay? There's going to be a two-part. The part one is the composition design, okay? The part two is the heat treatment design. Talking about 91, you know the 91 has a certain composition, and also 91 has a designated heat treatment schedule, normalized tempering or quench and tempering, okay? Now let's talk about the chemical composition of steel, okay? So when we talk about composition, then I have to talk about a strengthening mechanism. I'm not going to make you guys to be the metallurgists. I'm going to touch upon on this very quick. Okay, so normally there's a three common use strengthening mechanism. One is called a solid solution. It's like you put the sugar into the water. Okay. The second one is called precipitation. Okay, it's like the particles come out of the microstructure. Okay. Third one is called soft grain strengthening mechanism. This is basically become a significant when the monazite structure has been generated. Okay. When you create a certain steel, when you put an atom in there, you also set up a phase transformation behavior. Okay, so later on we're going to talk about it. Is the CCT diagram. Okay, so composition, microstructure. So before we go to the next slide talking about heat treatment, I'd like to introduce a little bit is what's the common steels family we normally facing. Okay, carbon steels. Okay, alloy steels, it can be carbon moly, core moly, core moly V, micro alloy steels, high stress, low alloy steels, many. And also we talk about stent steels. Okay, so stent steel can be austenitic, ferritic, monocytic, duplex. Okay, and also there's another kind of precipitation hardened stent steel. Okay. And also in our daily life, we also run into a lot of specs. Okay, commonly we're going to say is ASTM specs, AISI or ISAE specs, okay, or ASME specs. Okay, so each spec is dedicated by the type of steels, form of steels, many different factors. Okay, so if you doing the manufacture, you have to getting familiar with all of this specifications and codes. Okay, heat treatment. Okay, during the heat treatment, we basically do two things. Okay, so you're heating a steel up to a certain temperature. Okay, so if we do the annealings, normalizing, and quenching, then you have to heating the steel above upper critical temperature. They call it AC3 on heating. Okay, so this procedure is called austenitization. Okay, then follow up, you can do another heat treatment called tempering. Okay, tempering is running at a temperature below the lower critical temperature. I'm going to talk about what's the A1, what is the AC after. So all of this heat treatment, the main core from the metallurgical standpoint is controlled by the diffusion. Okay, so let's recap what we have been talking about it. Okay, so when people or when metallurgists design a steel, they design a microstructure. Okay, the microstructure is achieved by design a composition and a heat treatment. Okay, so when the composition is still with the composition, when you heat treat it properly, then you can achieve this microstructure. The microstructure gives the steels design the mechanical properties. Okay, so when we talk about the mechanical properties, it can be tensils, toughness, fatigue, creep, corrosion, wear, whatever is the design component it's going to be used for. Okay. Now, to understanding the steel regarding the heat treatment, we have to go back one more step, talking about allotropic iron. So what is allotropic means in the metallurgy, meaning is one pure metal, when you heat it up, so the metal will changing the crystal structure. Okay, using iron as one example, the iron at room temperature, the crystal structure is a BCC, body center cubic. Okay, so it's like we saw over here, this cubic center, in addition to 8 at the corner, is the 1 in the center. Okay, when you heat it up to 911 Celsius, it's changing to another structure called a gamma iron. So there's a face center cubic. Okay, so if you keep heating up to 1400 Celsius, it's changing back to a body center cubic structure again with a different lateral spacing. Okay, so this is the base why iron can be heat treated. Okay, but you say, well, Joe, the austenitic stainless steel is not heat treatable. So because it's fully austenite. Okay, so when you adding alloy to the iron, you will changing the phase transformation behavior. Okay, now what is steel? Okay, a lot of people keep asking the same question. So when we talk about steel, then we have to talk about the iron carbon phase diagram. Okay, so I have to establish a baseline. This diagram is being generated under equilibrium condition. So what that means is the heating and the cooling on this diagram is indefinitely slow. Okay, so people make this test, okay, for different alloys. Okay, so on this diagram, you can see this diagram separated by 2 parts. The part 1 is from 0 carbon to 2.11 carbon. That's called a steel. Okay, from 2.11 to 6.67, that's the cast iron. Okay, so that's the cast iron. So that's the common material we are using in our daily life. Okay, in here we see a 2 temperatures. One called A1, lower critical phase transformation temperature. That's this horizontal line. Okay, and we have a A3, that's the upper critical phase transformation temperature. That's this slope line over here. Okay, so this is the typical terminology in your daily life. You probably hear people going to talk about it. Okay, especially when you're dealing with the green iron material. So, okay, when you do the post-wall heat treatment, okay, so you hear, okay, these terminologies. Okay, quickly going through this. Okay, so what is the center cubic? Okay, so it looks like on the bottom. Okay, so the top is the face center cubic. Okay, so it's not what you see in the austenitic stainless steel. The microstructure showing like on the right. So the bottom, okay, is the BCC, is the ferrite. So showing as over here, the white face. Okay, that's the ferrite. Okay, so this slide is showing you for steel what's going to be happening when you're heating up. Okay, like a 0.4 carbon when you're heating up. Okay, so what happening? Okay, so when you pass A1 during the heating, then you begin to generate the austenite. Okay, so when you pass A3, the entire steel become austenite. Okay, vice versa, when you're cooling down from the austenite, then when you pass 3, then beginning to forming the ferrite. Okay, then keep going. When you pass A3, okay, then you forming a ferrite. Also, same time you're forming another phase called a pearlite. Okay, or ferrite plus lavender cementite. Okay. Okay, So this is the common microstructure the steel going to have. One is called pearlite. Okay, so this is basically mixture of ferrite. Ferrite is the matrix with the laminar cementite. Okay. Okay, so this phase is forming by fully diffusion controlled. Okay, so I'm going to explain that later. Okay, the bainite is also is a mixture of ferrite with a needle-like cementite. Okay, so you see the only changing is the precipitate changing the shape from a laminar to needle. Okay, so bainite is semi-diffuse controlled structure. What that meaning is when the bainite forming, the 50% of the needle will come out as a precipitate. The other 50% will come out during a tempering. Okay, so that's the reason very commonly as a T11, T22, we are not using bainite, we are using tempered bainite. Okay, martensite is completely different. Okay, martensite is a supersaturated solid solution. Okay, so there's no precipitate, so there's no cementite. Okay, basically in there, so this is a diffusionless constituents. Okay, so the structure is slightly different, called body center tetragonal. Okay, so if we are doing a tempering, forming a tempering martensite, so the microstructure is mixture of ferrite with tiny cementite. So if you add alloy in there, then you're forming a lot of different precipitates. Okay. Okay. So this is common, say, pearlite. So this is a common bainite. Bainite can be determined is upper bainite or lower bainite, depending on forming temperature. Okay, either forming 350 to 550, that's basically the upper, or below, that's a lower bainite. Okay, I'm not going to touch. Okay, martensite. Okay, martensite appearance is significantly influenced by the carbon content. Okay, so you can see on the bottom three pictures, when you from 0.2 to 0.6 to 1.2. Okay, so you can see the martensite changing the lace structure. On the upper corner, that one is 3.2 carbon. Okay, so that is coming from quenching cast iron. Okay. Okay. Now I got an issue. Okay, so you talk about the pearlite, you talk about the bainite, talk about the martensite, but on this iron carbon phase diagram, there's no bainite or no martensite. Okay, so where is bainite and martensite come from? Okay, so we have to emphasize the iron carbon phase diagram is equilibrium diagram. So meaning is your cooling rate is definitely slow. Okay, so that's very common in some of the iron carbon diagram. You see people labeled pearlite on there because pearlite is slow cooling microstructure. By definition, that's still not 100% correct. Okay, so so now what happening if you have the same steel? Okay, so if you're cooling fast, okay, so if you're cooling fast, then the transmission behavior is going to be shown differently, as you can see on the equilibrium phase diagram. Okay, so now we're going to talk about the CCT diagram. Okay, continuous cooling transformation diagram. Okay, so this is a common diagram people are using for in the industry. Okay, one thing I want to emphasize is called a critical cooling rate. Okay, so there's a several critical cooling rate over here. Okay, one is 0.3. That's the critical cooling rate to avoid forming ferrite or pearlite. Okay, so there's another one is 8.3. So that's a critical cooling rate. So if the cooling rate is faster than that, you're not going to form in bainite. Okay, so you can see if you're cooling at a different cooling rate, you will generate a different microstructure. Okay. The other phase diagram called the TDT diagram. Okay, time temperature transformation. Okay, so what people do in this is for certain microstructure, people like to heat treat it slightly different. Okay, people like to quenching these things down, say still down to a certain temperature, then holding it constantly at a constant temperature. Okay, let the phase transformation occur, just like people drawing on this red line, green line, or blue line. So they can perfectly control how much bainite, how much martensite you will forming in this steel. Okay, so this is different methodology to do the heat treatment. So let's talk about slightly on alloy effect. Okay, so I try to using these three CCT diagrams. Okay, as one example. You can see the very left one is one chrome, basically. That's equivalent to T11. The middle one is T22. The right-hand side one is the green 91, okay, or 9 chrome moly. Okay, you can see this CCT diagram is completely different. Okay, 1 1/4, you have a lot of ferrite forming, bainite forming, and martensite. When you increase alloy content from 1 1/4 to 2 1/4, you are moving the upper transmission ferrite to the right-hand side. Okay, you are enlarge the bainite area. That's the reason when you compare T11 to the T22, you see a more bainite colony in the microstructure. See, when you go into the 9 chrome, you see the entire area was martensite. Okay, so when you heat treat it at a normal cooling rate, you will see a martensite structure. Okay, I'm going to jump through this. Okay. The key on the heat treatment or on the phase transformation is the diffusion. Okay, so what people try to do is people try to control the cooling rate for a given steel, try to changing the precipitate shapes and the distribution. Okay, so the diffusion is the key. So if you want to heat treat this steel correctly, you have to allow the diffusion occur at a given temperature for sufficient time. What happened? Come on. Apologize. Okay. Now, for the uncooling transformation, okay, I say in the past is we are control the cooling rate. Okay, so when we control the cooling rate, then we control the precipitates. So in the carbon steel, so you see all the precipitates is laminar. Okay, so there's a laminar when you're cooling down, everything already forming. Okay, so then if you do the tempering on that, you are not going to changing the structure very much. Okay, so you're making it degraded slightly. Okay. But for the bainite structure, okay, it's a semi-diffused, okay, then 50% of the precipitate is already coming when bainite forming. The other 50% are still waiting for coming. You can use in control tempering to bring the other 50% out as the design. Okay, so you can put whatever the precipitate into a certain locations, control their size, control their interface structure. Okay. Martensite is completely different. Okay, martensite, when you're forming martensite is a super saturated structure. Nothing come out. Okay, so this is giving a metallurgist a full opportunity by using tempering to control the precipitation behavior. Okay, you can put through alloying, you can add a different alloying elements in there. You can control what precipitate is going to be forming in the matrix, what is the precipitate going to forming on the grain boundary, and how much do you want it, and what type of the precipitate will forming in each different location. Okay, so this is give you the optimum control of the material's property. Okay, so try to review one more time. Okay, so this I showed in before. Okay, this is the grade 91 microstructure at a different magnetization. Okay, the left hand side is 1,000, the middle is 10,000, and the right hand side is 50,000. Okay, so at the 10,000 you barely see the substructure, and at the 50,000 you can see very clearly. You can see all the particles in the wire forming. Then you can do additional study to determine what is the precipitate. You can also measure the size. You can study the interface structure. Okay. Now, let's talk about what's the difference between grade 91 and a traditional chromoly steel. Okay. This is a typical conversation showing for T2, T5, T9, T11, T12, T22, T91. Okay, so you can see not only chrome difference, moly difference, also grade 91 is tightly control the vanadium. It also control the niobium, control the nitrogen, and also limited nickels, and also control the aluminum. So that's a slightly complicated conversation. Okay, so if later on, if you're looking for the other members of creep stress enhanced ferritic steels, you are facing 92. You're facing 93, also called a SAVE 12AD. Okay. Recently, China has a new monocytic, steels called a G115. Okay. So their alloying system is much more complicated in the T91. So the T91 is so important. Is if you cannot understanding the T91, you will not going to understanding the rest of the higher grade. Okay? Because the alloying system are different. Okay. So their transformation behavior are different. Okay. So start from the left. That's basically, that is a grade 11. The middle one is grade 22. The right hand side is grade 91. Okay, so you're changing the alloy content, then you're changing the transformation behavior. Okay, then what you're gonna do is when you going through the design, the heat treatment, then you are changing the microstructure. Okay. So when you're forming a different microstructure, then you have a different mechanical properties. Okay, so this slide gave you, okay, you see what is the 22 is. Okay, the 22 creep stress. Okay, the 22 creep stress at 600 Celsius is only 35 megapascal, and the 91 is 100. Okay, because you changing the alloy system, you create a different microstructure. Okay, then you again a different level of the mechanical properties. Okay, people using monazite structures to achieve the optimum properties. Okay, is because the monazite is a supersaturated solid solution. Okay, so it's not only saturated with the carbon, it's also saturated with all other alloy elements. So what this thing is going to do is going to give the metallurgist the opportunity through a tempering to control how the precipitates to come out to achieve the best mechanical property. So in another word is, the 91 to again this beautiful mechanical properties is by generate a unique microstructure going through tightly controlled composition and tightly control the heat treatment. Okay. Now, the big challenge to all the OEMs or everybody handling the 91 or every creep strength enhanced fabric materials is how to maintain the proper microstructure. Okay, so at the beginning we talk about it. Okay, so the microstructure gives you the property. Okay, but during the manufacture of any component, you are going to do cold or hot forming, you're going to do weldings, also you will do a heat treatment. All of these procedures has the opportunity to change in the green 91 microstructure. That's the reason a lot of people hate to handle T91. The reason is very simple. The traditional manufacturer practice procedures when you're handling T11 and T22, many things you cannot do to the 91, okay, because they have a different microstructure, okay. Some of the behavior, for example, local torch heating, okay, your torch heat T11 is probably okay because the microstructure is titanium can tolerate much more uncontrolled heating, but the 91 is not. So if you uncontrolled heat the 91 with the torch, okay, likely you will kill the green 91, okay. So that's the reason, okay, Jeff and I wrote the first guideline for APRATE, okay. So I think that this guideline has been upgraded by Jonathan Parker later, okay. This version of the guideline basically is started with a three-part, okay. One is a fundamental understanding of the green 91, okay. Two is fundamental understanding of the manufacture procedures, okay, for all the power generation equipment, what you normally do in the shop, okay. So what this each procedure is going to influence on green 91 material, and also including accumulated experience and understanding the common mistakes people will make during the manufacture of green 91. Okay, this is through research and also through failure analysis. Okay, so basically that's what the captured is the fundamental metallurgy of the green 91. The key is microstructure of the green 91. Whenever you changing the green 91 microstructure, you changing the property of the green 91 component. Okay, so that's the key. So for any component in service, okay, so here is the question for you. Do you know your green 91 component is in the proper metallurgical condition? Okay, so this is everybody facing. Okay, I'm using green 91, but I have no idea what the conditions of my green 91. Okay, so if you are not so sure, do you know what you should do about it? Okay, so this question will lead to for Dave to give the next talks on the how to inspect the green 91. Thank you.
Thank you, Dr. New. That was very enlightening. I'm going to talk about the basically inspection and condition assessment of grade 91. Obviously, Dr. Joe covered the metallurgical part very well. Because of what he's talked about, there's a lot of the standard methods for that you use for inspection and assessment of T91 is different than most other metals. So with that, we start screen share. All right, so I will jump through some of these because they're repeats of what Dr. Jones already spoken of. So let's see, let's move on. Some great pictures in here. So here's our buddy Albert. Okay. Inspection challenge. The enhanced properties of the CSEF steels can only be realized if the appropriate condition of microstructure obtained through the normal normalizing and tempering operation maintained through all stages of the process. Yeah, that is where the uniqueness of T91 comes into effect. Obviously, you learned about the microstructure being tempered martensite. In the absence of the critical precipitate network to stabilize the disordered martenite structure, the material reverts something to kin of grade 9. So yeah, what's saying here is if the proper procedures aren't used, you might as well just skip 91 and just use grade 9. This is just showing, again, this is some repeats of what Dr. Joe is showing, but yeah, this is showing the tempered martenite substructure. The important issue when you're dealing with field assessment inspection is because precipitate substructure cannot be assessed at these magnifications, there is no guarantee that what you see, say from replication, will be a good representation of what is in the material subsurface. I'll skip through this here. Here's a diagram showing what I just mentioned earlier. Basically, your 91 allowable stress is up here, and 9 if your procedures aren't followed properly, your allowable properties drop significantly back to typical T9 material versus a T91. Okay, now I get the meat of the matter here. Basically, the non-destructive tools that we currently use when we go out in the field are not, and in this case, particular hardness testing and replication, are incapable of directly measuring these features at the microstructure that govern the material's long-term creep strength. That is, you can have properties that are still good, except your creep strength will be degraded significantly. And Dr. Joe mentioned a few things about composition, obviously chemistry effects, nitrogen, aluminum, all these things affect the influence and stability of the precipitates in the material. So, in cases where improper processing has destroyed the tempered martensitic structure, resulting in structure of ferrite and carbides with low hardness, then hardness testing replication can be effective methods for detecting the defective condition. If the defective areas can be found, testing is performed properly. Grade 91 has the tempered martenite structure. And as long as that process or if the process was never developed and disrupted, obviously you end up with poor long-term creep properties. So just a little bit about hardness testing. We've all seen we all know about hardness testing. We know basically how it works, and there's a direct relationship, of course, between or approximate relationship between hardness and tensile strength. But again, tensile strength only tells us part of the story. It doesn't tell us what anything about the creep properties of the material. So, and here's this is a slide that you'll see quite a few times in here. This is really where this is what's most important. You know, the use of hardness testing as a QC tool to predict long-term creep strength rests on 3 critical assumptions. And obviously the composition. The material has favorable chemical composition. Material is properly normalized, and material has not been heat treated above AC1 temperature. So you remember those, because that's kind of the driver between, or really what drives why typical condition assessment tools may not give you a good, adequate idea of the condition of the material. A little bit more about hardness. It's very interesting. Apparently the original material specifications based on tensile strength and hardness show 85 KSI for 91, which is only a 174 Rockwell B hardness. A lot of people think that that number is way too low, and I'll go to this slide here. This is kind of interesting. At a hardness level of 190, Rockwell B material should always possess an acceptable structure if the 3 conditions described in the preceding slide have been met. But what I find interesting here is, this is, ASME. We're down here at 185. The European code EN is actually stricter requirements, and it's showing around 200 Rockwell B, which is closer to really where I think Dr. Joe thinks we need to be. And again, here this shows up often in these slides here. It's talking about below a hardness of 190 or some similar level, the material may be acceptable. But further investigation through metallurgical replication is prudent to verify the structure. But again, it's all based on if these 3 requirements are met: chemical composition, whether it was properly normalized, and making sure that the material has not been heated above AC1 during the normalizing treatment. Just a little bit more about hardness. We've all seen all the correlations between different hardness scales, the Rockwell, the Vickers, the Brunels, and there is a lot of discrepancy. So this is just one more factor that introduces inaccuracies in the analysis results. Is that when we do try to convert, we see numbers that may not be the same, or sometimes not even very close between the different hardness scales. This is just showing the Brunel and Vickers. Okay, then we get into some of the logistics of actually doing the hardness testing. And this applies not only to 91, but applies to all materials. Obviously, there's different types of material testers. Going to the Intel Brunel is pretty primitive, but it actually provides reasonable accurate results because of the magnitude of the load applied. One of the key things in all these is decarbonization, which occurs during the heating process. And I'll show you some slides here in just a second, what I'm saying there. The MiG-20s, very popular method used nowadays to get hardness, but it is difficult to use, and it's very sensitive to surface effects. This just shows the Brunel, crude but effective. And there's the MiG-20, high tech, very sensitive to surface conditions. And there's the Equitech. So yeah, for most testing methods, a certain amount of preparation surfaces are required to remove the surface oxide and improve the surface roughness, decarbonization is a big issue, and all you're getting, as you know, is on these portable hardness testers, just this surface hardness. Again, decarbonization depth can vary from a few thousandths as much as 80 to 100 thousandths. The affected depth includes both a fully decarbonized region and a depleted region. And this slide here will show you as you go through the substrate, you're talking 144 will be at the surface due to decarbonization, and down here at this depth, which I don't have a scale on here, but it's basically 200 HB. So you're using this portable tester, and this is what you're going to be measuring up here. It's no indication of what the body of the material actually is in hardness. Quickly, some common places, just to remember when you're doing hardness testing, you want to get multiple locations. Obviously, you want to get in the base material, the substrate. You want to get in the weld itself, and you want to get plenty of representative samples. And depending on the OD of the pipe or tube, this kind of tells you how many points that you want to get along the circumference of the pipe. Just some more examples: elbows. Some examples of test locations. Here's one: lugs. Around lugs. One of the key things when you're looking at hardness in any material really is you want to look at not only the absolute number at each location, but the delta between these numbers can tell you a lot about the condition of the material. If you're running go back up here, say in the weld there, if you're running a 210 versus a 160, those variances in the hardness readings can tell you a lot. It's actually sometimes more important than the absolute value itself. Now, replication, next thing, can be an effective tool for determining general structure of material. Basically, whether the structure is tempered, martensite, or ferrite and carbides. But for reasons already discussed, confirmation of tempered martenite structure through replication does not ensure acceptable creep properties. Of course, replication is limited to surface or near surface applications. So the through thickness variations in structure due to steep temperature gradients will not be detected. Decarbonization affects this substantially the values, and same as with hardness. Metallographic replication has its own issues. There's a very high level of skill required to properly prepare a test surface. A lot of people think they know how to do replication, and one of the issues is, if you take a replica out in the field and it's not done properly, and you take it back into the lab itself, there's no second chance of getting that information. So it has to be done right the first time. So the understanding of basic metallographic techniques is essential. The grinding, polishing is important. Etching is important. And sometimes just getting to some areas are very difficult. The number of technical specialists who have both a strong background in interpretation and who understand the metallurgy of these steels is limited. Moving on here, this is just showing again, Dr. Joey's showing quite a few of these, but this is showing material basically consisting of ferrite and large carbides. And you can see here has pretty low hardness. Here's one with a pretty normal tempered martenite structure, and you're sitting there at 210 Rockwell B, which is where you want to be. Let's see, I'll skip through these. This is kind of showing the incredible degradation of material life, creep life. Here's one that's estimated to be 20,000 hours and actually ruptured after only 287 hours. Here's one that ruptured after 388 hours. So really the dilemma is numerous design and processing errors have occurred during the implementation of CSEF steels, as demonstrated both by premature failures and result in a large number of inspections. These deficiencies can be localized with long-term creep properties substantially reduced by factors much as 10. The standard warranties. Standard warranties were not to protect end users from the vast majority of problems, and that's important. Generally, if you really, unless you really tailor your warranties on material towards some of these abnormal conditions with 91. You're probably not going to be covered under, like it says there, under the vast majority of problems. So what can really be done about this? In view of the limitations described above for hardness testing and replication, is it worth testing components that have been installed? And basically, the answer is yes. Some information is better. It's just you have to use that information in a way that takes into account the limitations of this data. This is an example right here. It's kind of showing here, if you're out there, you do your test, you do your hardness testing, and your hardness is bad, it doesn't really make a whole lot of difference about the microstructure. It's probably going to be unacceptable. However, if your hardness is good, microstructure even can be questionable and you can consider it acceptable. Obviously, if your hardness and your microstructure is good, you can consider that acceptable with a pretty high confidence level of greater than 85%. And even with all this data, this is the assessment of assumed or tested properties under actual operating conditions may show that some level of serviceability exists. And this kind of gets into, cover just a little bit here in a few minutes, but it all depends on, this particular location of material that's being tested and how, what kind of stresses are applied to it and what temperature and pressure. If it's operated way below its design pressure temperature, obviously you have a lot more flexibility to say, yes, this material is acceptable. And temperature and out the stress points too. Yeah, if you're in a high stress location, that's going to dictate whether you determine this material to be usable and acceptable versus not. Mitigating risks, to the extent possible, determine the existing condition of components based on review of available information, including CMTRs, fabrication records, construction records, monitor, repair, replace components with deficient properties. Finding bad material does not always require immediate replacement. That's what I'm saying. It depends on where it's operating, where it's relative to its design, what kind of stresses are on it. We did an assessment for a utility last year where they determined, and T91 piping, where they determined that the piping was sufficiently in a state where it was acceptable to operate, but some of the T's and elbows were not. So they made a decision to replace just just certain T's and elbows based on the not only the assessment results, but basically a life assessment based on pressure, temperature, and stresses. Obviously, if you have new units, which a lot of you don't, a lot of you are operating components that have been in service for quite a while, and you don't have the original documentation. But if you have new units, obviously you want to do initial design review, soundness, material procurement. You want to specify optimum chemistry, heat treatment, and you want the complete control during the fabrication process. And that's basically talking about, outside surveillance by a fabricator of the fabricator. Let's see, skipping here just a little bit. Okay, inspection summary. The corrosion, creep strength enhanced ferritic steels are complex alloys that require a high level of control in all phases of processing if the enhanced creep properties are to be achieved. Where the processing history has not been fully documented, existing non-destructive inspection techniques cannot be in every case distinguish good material from deficient material. In the absence of a comprehensive data package documenting the pedigree of each component, end users are burdened with a high level of risk if virtually impossible to quantify. Implementation of an aggressive quality control program. The results of the inspections and testing conducted in part of a QC program become the basis for the life assessment that monitor the condition of the components that service is accumulated. And of course, the ultimate goal is the safe, reliable operation of the equipment. In the case of the utility that I mentioned earlier, they chose not to do extensive further assessment, say destructive assessment. To them, it came out really to be cheaper just to replace it, or cheaper, easier just to replace the component rather than to come up with some program of monitoring and for future repair. Skip that a little bit. Real quickly, I'll finish up here. What should be done when damage or deficient material is found? It's not always the case that when damage or deficient material is found, the unit must remain offline until components are replaced. The condition of the material should be evaluated with respect to the specific operating conditions for that particular component and the operating conditions that are expected to prevail during future operation. That's what I mentioned earlier. There are, obviously the components have been operated a certain condition, and you look at that pressure, temperature, stresses, but you could also use that opportunity to say, maybe derate the unit and say, well, we're gonna continue to operate with these components, but we're gonna back off on steam temperature, so to reduce the operating stresses. For the initial assessment, assume worst case. If the result indicates a substantial amount of remaining life, monitor the future operation of the component to confirm initial assessment. If the life calculation, assuming worst case properties, indicates limited life, then consider sampling to more accurately define actual material properties. So say, obviously, that would be the best way to determine the actual properties versus field techniques. Sometimes that gets very expensive, and that's the kind of thing you have to weigh out to determine whether it's worth it to do the additional testing or just to replace the component. Let's see. Move on here. There's some additional things that can be done. Just cover this real quickly here. The results of non-destructive testing indicate significant damage or deficiency. It says destructive testing can be used to quantify the level of damage and the impact on remaining life. The most common destructive test method is creep or stress rupture testing. And here it's creep indentation testing is sample potentially non-destructive. Monitor creep strain to locate material within database scatter band. Most effective when comparing an unknown material to known material. And get the answer pretty quick. And this second option would be to instrument the unit with either thermocouples and or strain gauges. Here's just a quick picture of the creep indentation testing. Basically, it's kind of like a hardness testing, but it's done at a temperature, a high temperature. Here's an example of some strain gauges installed, some piping. So in summary here, when deficient material is uncovered and if a component cannot be easily repaired or replaced, initiate staged assessment to establish the level of concern regarding future operation of the component in its existing condition. Assume worst case condition. Can it continue to operate reliably for a substantial period of time? If yes, then you can instrument it. If no, whether the component can operate reliably for a limited period of time. Then initiate destructive testing to more accurately establish the material's creep strength. If the analysis indicates material cannot operate reliably for even a limited time with design conditions, determine if reduced operating conditions can provide a limited period of safe operation. That's what I mentioned earlier. Basically, that includes reduction of temperature, reduction of pressure, operating pressure, and sometimes can also be maybe some temporary type supports to reduce the stresses. So with that, I am done. So let's see, let's see if we have any questions. There's no questions in the chat, so does anybody have any questions? I'll unmute. Let's see. Get it right. So I've unmuted everybody. So if you have any questions, please ask them or put them in the chat.
No questions?
Well, either we did a good job or a bad job.
Dave, what is the meaning of life?
You have to watch Monty Python movies.
I think you were very thorough. That's why there's no questions. You've done a very thorough job, I believe.
Nope, there's no other questions. Like I mentioned at the very beginning, we hope to have many more of these webinars set up. We're looking at not only, webinars on metallurgy such as this one, materials, possibly failure analysis, case examples of root cause analysis. So, and everything I mentioned at the very beginning, some of you weren't on there, but if you weren't on the original email distribution list and you'd like to be added, put your name and contact information in the chat there, and we'll add you to it next. So you'll be ready for the next webinar.
Dave.
Yes, sir.
I'm going to add up for the futures webinars. We are not only going to talk about the case study. I think I was talking with Jeff. We're going to probably talking about code activities also. Okay, talking about the allowable stress, reducing how it's influence on the design, how the influence on the current construction equipment, how it's going to influence on the in-service component. Okay, so we're going to talk about Green 91 DMW failures. We also can talk about the Green 91 base metal quality issues. Okay, so we have 100 cases of Green 91 failures. Depend on our audience which part of the failure mechanism everybody going to be interested in. You can send us by emails, by whatever means. Okay, so let us know. Then we can reconstruct the follow-up webinars based on everybody's interest.
Sounds good. Yeah. So yeah, if you have, yeah, what Joe's saying is if you have something of interest that you'd like to hear about in this area, shoot us an email. My email address is dnesbitt@atc-tn.com.
Or you can go to ATC, that's a CES website to send either to me or send to Jeff.
Right.
Yeah.
So, yeah, lots of ways you can contact us. We'd love to hear, your ideas on future webinars. We're doing this for you guys out in the industry, so want to give you what you need and what you desire. So
yeah, this is just the first one.
Yeah, so we had a few technical glitches, but we did pretty good for the first one.
Okay.
All right. Thank you, everyone.
Thank you. Enjoyed it.
Thank you. Good night, guys in China.
Good night, John Boy.